So entropy is simply composed of undesired heat changes, which if I'm assuming for a reversible process is equal to 0, but for an irreversible process, if this is irreversible, what is the relationship to 0?
Greater than.
Well, yes, sort of, but it's actually entropy ends up being negative, so it's less than 0. Because it depends on where you're going. It's actually a heat loss. So it's undesired heat loss. So we went from a heat transfer to an engine to work. Then what happened is you got heat being lost from it. So it's entropy in the negative energy side of things. It wasn't planned on. Okay, so that's why it's less than 0, but it makes sense it's not equal to 0. And from this, primarily ds is equal to Q, which is your entropy, over T for a reversible process. So let's outline it. Let's do a quick example on this. Let's say if I have a PV diagram, pressure versus volume diagram, and I have two stages. I have stage 1 and I have stage 2. So going from stage 1 to stage 2, think of that heat engine that we just applied heat to, for example. Well, this is an irreversible process because I'm going to have heat being lost. So it's an irreversible process, which is this right here. However, if somehow magically I could do a reversible process to bring 2 to 1 again, this is what the closed path will be, and this will be reversible. So let's apply it for this cycle. So for this cycle, the integral of delta Q over temperature is going to be less than 0 by definition, because I have an irreversibility as part of this cycle. Now, part of it is reversible and part of it is irreversible. So let's expand the derivative, the integral. So the integral will go from 1 to 2, which is my irreversible process. So Q, the rate of change of heat over temperature, plus going back the integral from 2 to 1. So this is my closed loop system. And this process will be the reversible process. And this is going to be less than or equal to 0. If this is a reversible process, then, well, it's equal to 0. But if it's not a reversible process, then this has to be less than 0. So, well, this is the same as this, so I could just take the integral of ds, which I will get the integral of 2(1) q over t plus s1 minus s2 has to be less than or equal to 0. Okay. So rearrange my terms. And what am I end up getting? Am I going to end up s2 minus s1 is greater than or equal to my integral from 1 to 2 q over t of my irreversible process. And hence that's why entropy is actually in the negative. Now, I don't want to deal with greater than and so forth. What if I want to make it a generic equation so that I can handle the rate of change of entropy? So I could say S2 minus S1 is equal to my integral from 1 to 2 Q over T plus S generated, the entropy generated as part of the process. And S gen has to be greater than 0. Okay? And that's the final equation, and that's where you get your entropy equation. So most likely, in the past, you were given this equation and like, here's entropy. That's it. But now you understand how it's sort of derived, in a sense, given a closed loop cycle, you could visualize the rate of change of entropy. Okay? All right, so moving on, let's try to apply. So this is a restrictive equation for my first law. I can't just blindly apply my thermodynamics first law. I have to account for this. So that means I have to apply conservation to this as well. And that's what we're going to do next, is for a closed loop system, apply the same conservations that we have. So right here, I'm going to use this equation and say for a closed system, so we said S2 minus S1 is equal to my interval 1 to 2 of Q over temperature plus Sgen. Now, entropy, just for unit's sake, is kilojoules per Kelvin. Heat over temperature. It's undesired heat loss. It wasn't planned. So if I take it in a rate form, for time, well, simply a substantial derivative of the entropy over time is equal to, this is in terms of heat, well, integral. So I will say the summation of Q in over T, whatever I define as a nominal T temperature, minus out, Q out, the rate of that, over T nominal, plus Sgen. So let's apply our Reynolds transport theorem to it. ds over dt is equal to d over dt, the control volume integral of my entropy times its mass. Dt over here is mass flow, is equal to minus my integral of what goes in versus what goes out of my control surface, which is rho entropy multiplied by my velocity vector, the normal component, multiplied by my area that I'm defining as an input and output of my control volume. Same exact Reynolds transfer theorem that we've been applying so far. In Q in over T naught minus out Q out over T naught plus Sgen, the generated entropy as part of the process. So from that, I could just outline my general form of the equation, which that's all we care about, is 1D flow, steady state. Well, that's going to be, this term is going to go to 0 because it's not dependent on it anymore. So 0 is equal to, well, I want to track what goes in and what goes out, so it's simply the summation of inlet of m dot in, entropy in, minus the summation of outlet m dot out, s out, plus my summation of in, q in, over t naught, minus out, q out, over t naught, plus s gen. And this is my general form of the equation that I need to worry about. And I'm trying to track entropy changes.
That should be ds times.
So, based on this equation, we can now go and define my isentropic process, where entropy is actually equals to 0. Now, this is, you've seen this in high-speed aero, didn't you? Or no?
No.
Okay. But you know your tables are isentropic tables. How did you use your tables for your equations? Yes. Okay. All right. So, well, we're revising it. Did you use tables or did you use equations to solve problems for high-speed aero?
Tables.
That's going to hurt us.
Tables
So,
and ratios.
so tables are great in the sense of appreciating values. I like using the tables. However, you will come to realize for propulsion systems, and probably you agonize over it when you're trying to solve problems. You're trying to get a Mach number, and that Mach number ends up in between the table numbers. Let's say A over A star you're trying to get, or stagnation pressure over static pressure, and it ends up being in between values. Or maybe you went to the table in an exam and you pulled up a value and you just went to the line under it, and your final answer ended up being incorrect, and that's where you get hurt quite a bit. So I understand that. In propulsion systems, we cannot use tables because guess what? You're dealing with a dynamic engine. Things keep changing all the time. So your stagnation pressure changes because your compressor changes, your flight Mach number changes, so we're not going to use tables. You could use them as a reference since you're used to it, but we're always going to have to use equations to drive our engine simulation. 1 second. And also, based on that, you're going to have to use the equations primarily in the isentropic form, and that's what we're going to drive shortly. So we had a question?
Yeah, what is the engine?
What?
Esgen? Is it
It's just the entropy generated due an irreversible process. That's clear to everybody, right? This is an irreversible process that I have right here. This is an irreversible process. This is something that I could make this equal to, right? So this is greater than this. I just want to make it equal. So I'm just going to say it's entropy generated. Some quantity that I'm going to figure out. Okay? Good question. All right, so given this equation, let's define our TDS equation so that, or TDS relations, so we can use it in the isentropic form of the equations. Don't get stressed out with all these equations because we're going to use it extensively. That you're going to see a significant amount of examples of how we're using it. So if you feel like, well, my foundation is not as strong because I'm seeing these equations for the first time, which you shouldn't be. If you're seeing it for the first time, it's not a good thing. But you should have seen it in fluids, you should have seen it in thermo, you should have seen it in high-speed aero. What else? Heat transfer. These equations repeat all the time, but we're going to be using these equations in a lot of example problems and all that, so you're going to end up using it in second nature. But anyway, TDS relations, we just said that Q is equal to TDS. Well, based on this, I could get my general form, which is TDS is equal to my internal energy plus P dV. Now, how did I get this? I already have the internal energy is equal to Q in plus work, in, for example, or rate of change of work. But I already know that this is equal to minus P dV, boundary work, like we talked. So if I substitute this, and I got my Q, substitute Q right here again, and this is how I end up with that equation. So this is the equation that I need to worry about. TS is equal to P dV. And we said this is equation 1. Okay, well, enthalpy. How do I relate it to enthalpy? You have to do this with thermo. You did high school? Ah, there you go. So somebody ratted you out. Said you did it in high school.
We didn't do the previous stuff, but we did do TDS.
Oh, so you did? Okay. Well, he probably just said this is the general form and just move on. But I wanted to explain how do you get this equation. Okay, entropy is, think of your car engine. You're trying to get work out of the car engine. You want everything to go to the wheels. But after you run your engine is hot. That's actual energy that is being lost that you're no longer recovering anymore. It's not going to useful work. It's just going to the ambient. Question?
Is it minus PdV?
Boundary work?
Well, it says on the top that work n is minus I squared.
It says on the top.
Right there.
In your first equation, he's asking is it plus
Right where
work
it's at.
in
Plus
minus
plus.
PdV or work in is
It depends on the convention of interest. I'm writing just what delta work in will be as an input, but you have to relate it to input versus output in your system. It's just a general form for now. So even if I want to make it plus, so if I go here and put it in and move it on this side, I will get everything positive. So I can substitute it here, so I have TDS is equal to this. But depends on your piston work. Positive or negative, I'm just using a convention right now that I'm going to assign negative. But it depends on whether I'm actually putting heat in, or I could be doing Q out.